So the last problem I have for you today is 29C5, which says to show that for each p prime, there is a field with p squared elements. And I like this problem because the method that we're going to use does generalize, and in fact, you will be able to prove that all powers of p can be realized as field extensions. The proof for higher degrees is slightly more involved if you want to do an on-the-nose generalization, but I think this is a nice problem because it gives the idea in a very accessible kind of way. And so without any further ado, let's take a look at how you can construct this thing. So the key is that we saw that if you have an FP, the thing to do is to construct a degree 2 extension. Because if I can find a way to do FP adjoin X modulo some degree 2 thing, that will, if it has degree 2, then I will have elements, right, 0, 1 through p minus 1, and then x plus 1, x plus p minus 1, 2x, right, 2x plus 1, and so on up to p minus 1x. Or maybe just said more succinctly, since it's a two-dimensional vector space, there's a p squared worth of them, p times p, right? P for the first coefficient, for the linear coefficient, p for the constant coefficient, times them together. Great. So that what I need to do is I need to prove that there is always, for any p, such an irreducible quadratic, right? Because this has to be irreducible. So the strategy is, how many reducible quadratics are there? Right, let's do some counting. We know that there are p squared total monic quadratics, right? Because I get to choose p things here and p things here. So there's p squared polynomials to work with. I need to prove that out of those p squared, at least one of them is irreducible. So if it was reducible, then it would factor, right? This would have to factor into ax plus b. Sorry, this ax plus b would have to factor into into x plus some new thing. Man, I keep accidentally triggering the writing. X plus c, x plus d. And the key is that both c and d live in FP, right? Because that's what it would mean to factor in FP. However, this is the same thing as x plus d times x plus c, right? It's symmetric. Multiplication is commutative. So what we're seeing is, while there are p squared ways to choose the roots in FP, there are only p squared over 2 resulting polynomials. And something has got to be wrong here because the p is odd in general. So hold on, where did I go wrong? Oh yeah, I'm stupid. I found my mistake. My mistake is that you don't have p squared total polynomials that you can work with. P squared ways of choosing the roots is true. P squared total monic quadratics is also true. But the issue is, oh wait, what is the issue? What I wanted to say is that you can't choose the constant term to be 0. Because if the constant term is 0, then what you get is obviously not irreducible. But that's not the issue. The issue is that this symmetry argument is secretly assuming they're different. So there are p squared ways of choosing the roots in FP, but some are the same. How many are the same? Well, if D and C are different, there are P times P minus 1 ways to choose distinct roots. And that's what I needed. That's always an even number. So that gives P times P minus 1 over 2, which polynomials. This is distinct reducible polynomials. Now that's if they have distinct roots. There are also P more with duplicate roots. Right? The expressions of the form x plus c squared when they have duplicate roots for c ranging over the values of fp. And so this gives a combined count of the reducible ones of p times p minus 1 over 2 plus p. Now the question is, how does that compare to p squared? Well, this is p squared minus p over 2. And then I could write this as 2p over 2 and combine them, or get p times p plus 1 over 2. And the question is, how does this compare to p squared? Well, perhaps a better way of writing it would be to say, if I want such a field to exist, then I want this number to be lesser. So if I want p times p plus 1 over 2 to be less than p squared, what do I learn about p? Well, I learned that p times p plus 1 is less than p squared, or p squared plus p, 2p squared. P squared plus p should be less than 2p squared, or p should be less than p squared. And of course, that is true once p is greater than 1, which is true since p is prime, right? P is at least 2. All right, there we go. We get it. Whew. Sorry, I got a little bit tangled up there and that, but that's okay. We figured it out. So this proves, what did we really do? We proved that the count of reducible polynomials is less than the count of all polynomials. Therefore, the difference, all polynomials minus the reducible ones, is positive, but these are exactly the irreducible ones. So this is a non-constructive proof that an irreducible polynomial exists. Hard work. Sorry for getting tripped up there, friends. All right, I think that's enough. Take a look at your homework problems, and if anything comes up, you guys know where to find me. Take care.